Alrighty, welcome everybody. Thanks for hanging out for this session. I'm going to be talking today about tracking and performance at Octopus Deploy. My name is Paul Gradie. I'm a software engineer, and yeah, thanks for coming here and hanging out for this event. This is pretty exciting, I think, for everybody. So it's the first time we've done this. I'm sure you've heard this a million times. Cool. All right. So the first thing we're going to do is just kind of go through the itinerary for what I'm going to talk about. We'll do some introductions. I'll give you a bit of background on myself as well as the team. Then we'll go through and kind of get into a little bit what we mean by performance. This is probably, you can interpret performance a few different ways. So we're going to focus in on the specific things that we're concerned with respect to this talk. Then we'll talk about, why do we care about tracking performance? What does this do for us internally as an organization? We've got a bit of a history behind this already. I've been at the company for a few years, and I've seen this kind of unfold over the last few years. So we'll go over a brief history of performance tracking at the company, talk about some of the things that we've done to try to achieve this in the past. Then we'll get into the nitty gritty of like what we're actually doing right now, which is the current performance tracking system. So we'll talk about that. I'll share some details around that. And then from there, we'll talk about some of the challenges, of course, with assessing performance in the way that we're trying to do this. And then we'll get into something that I think a lot of people hopefully will find pretty interesting, which is assessing scalability using machine learning. So that should hopefully be pretty cool towards the end of the talk. Okay, so first up, let's do some introductions. All right, so my name's Paul Gradie. Again, I'm a software engineer at the company. I have in a former life, I was a data scientist. And so I bring to bear some of my background in statistics to try to help solve some of our, some of the problems that we're finding in this space. But in support of this as well, we've got a whole bunch of people. We've got Ian Core, Matt Shepard, Nelson Suzanto, Bonnie Sang, Felix I, Sean Heavey, Dennis Kostenchuk, Matt Hilton, Rob Wagner. I'm giving shout outs to everybody here because they're all really important people and players in this space for us, helping us deliver a lot of value in terms of performance improvements, as well as a tracking system that we'll talk about. So first question, like what exactly do we mean by performance when we say performance? Like what exactly am I talking about? As you can imagine, there's a lot of ways to interpret this. In particular for this talk, I'm going to focus in on the idea of speed and scalability. So with speed, what I'm talking about is how quickly do requests return from the server, right? That's the main question. And the concern here is, mainly around preventing slowdowns from code changes. And immediately it probably becomes apparent as you think about this, that there's a lot of different ways that you could measure this. And, I've got a diagram here on the right to remind me about the different layers that you can kind of assess speed with, or speed at rather. So for example, you might be interested in how quickly does the UI respond when you click a button, when you, create a deployment, that sort of thing. The UI, the request or the user interaction with the UI will send a request to the API. The API will do its business and then return. And then you may be orchestrating things at the UI level. You can also look directly at the API surface. So you've got, for example, a client, you may be interacting with the API. You submit a request to update a thing. How long does it take to do that thing? And then just gauge kind of how long that takes. So you've got this idea of like, it becomes kind of complex, this idea of like, how fast do things go? And you've got multiple layers you can assess that. And so we're going to have to decide kind of where the value is for us to make that assessment about whether or not our code changes are causing our product to slow down. The other thing that we'll talk about is this idea of scalability, which is sort of asking the question, how well does Octopus Server operate when there's more data or more server activity? So as things get bigger, as you've got more tenants, as you've got more background processes, we've got a lot of stuff happening beneath the surface in an Octopus Server. Everyone's familiar probably with this idea of a task, the task queue. You kick off a deployment, it returns immediately, for example, but you may have 1,000 deployments that are just kind of sitting there being processed in the background. And so you get this idea where you've got like, what exactly am I interested in with respect to speed and scalability? Is there a lot of stuff happening? Is there a lot of pre-existing state on the server? Are we waiting for the response from the server for something like an update, or we've kicked off a task? How fast does that return? Do we have a lot of, or are we interested in waiting for that task to complete? How do we actually assess this problem? But this is the space that we're operating in with respect to the tracking system and the concepts we'll cover over in this talk. So this kind of begs the question, I suppose. Hopefully, this is somewhat self-evident, but in case it's not, why do we even care about tracking performance? I think it goes without saying that we're always thinking about how to make our product faster, and I think everybody cares when they're making code changes. Is this going to make things go slower? So why do we care about tracking this? We're always trying to make things faster. Well, the reality is that unfortunately, we ship regressions. Developers, engineers, we ship bugs. We ship changes that we're not always 100% sure what's going to be the impact of that change. And the reality at Octopus is that Octopus Server is constantly evolving. So I've got a list of things that we've done in the last few years that kind of illustrate some of the really fundamental changes that we've made. I think it's pretty obvious that we're always adding new features, we're making changes and tweaking features, but we're also doing a lot of stuff beneath the surface that fundamentally change how the product operates. So for example, we've recently finished a migration of web frameworks from NancyFX to ASP.NET. That was a huge, fundamental change in the way that the server is even built. We've introduced Git as a new persistence mechanism. So we've changed the entire persistence strategy, like how we save and access data in the database to support certain features, for example, like config as code. And in fact, when we first did this, we shipped a pretty bad regression and we didn't have visibility on that. We've changed large portions of the code base to be asynchronous. So I say large portions, not the entire thing. And so when you have the mixture of synchronous and asynchronous code, you can lead to interesting scenarios where there's contention for things like connections to the database and that sort of thing. And in the process of doing this, we have unfortunately shipped some regressions, things that led to deadlocks, or things that were almost deadlocks, where things become very slow as these resources are freed up, basically. We've been recently evolving our caching mechanisms. That's another good example of one of these broad impact changes. This is an interesting one because we actually measured the impact of this change. We determined that there was a slight regression, but we decided to ship it anyways because we felt that the value trade-off was there. And then currently what we're doing is we're migrating from a custom ORM, Nevermore, the thing that we use to actually interact with the database, to use Entity Framework. And so the big picture here is that all of these changes are vulnerable to performance regressions. And the problem that we have is that we don't really have a lot of good visibility on just even generally how well the product performs at any scale. So as we've thought about this over the last few years, and as we've made all of these changes, we've attempted things, right? We've had some successes, we've had some failures. And so what we're going to talk about next is a brief history of performance tracking at Octopus. And I'm going to keep this pretty high level, and we're just going to share sort of the main things that we've tried to kind of get us to where we are now. So a little bit of context first. Octopus tends to be a pretty lean company. We're not huge. We don't have thousands of engineers. And so whenever we try to attempt a solution, we tend to try to do, we try to go for like a high reusability or a co-opting type of approach. And so the first thing that we tried back in the day, this is a few years ago now, was we tried co-opting our end-to-end test framework. So what is the end-to-end test framework? It's a suite of tests that basically orchestrate complex behaviors, similar to like how a customer would use the product, basically. And the thing about the end-to-end test framework is that it's quite complex. And essentially what we do is we spin up like 6 or 8 instances of Octopus Server, and then we round robin them. And for each test, we say, cool, that one's available. Let's go and fire some requests at that server. And then we'll assert on some output from that. And so how we did this was we basically had a wrapper that sat on top of this really complex framework that would measure how long these requests took anytime we fired requests to the API. And again, this is on a machine that's got a lot of activity on it already, and so you're making these requests, singular requests, in ways that are basically locked into the design of the test itself. And you're making a single request. So the problem that we ran into was, first of all, it's like extremely difficult to maintain this thing, and it was very difficult to extend it. Because it's quite complex. It's fit for purpose. It's designed to be sort of a correctness test framework, and to sort of layer on top a performance element to that basically was it was just too difficult, frankly. And so, in addition to all the maintenance hassles, he had this high bias element where you've got all this noise on the machine. If you're doing performance tests or benchmarks, you're basically trying to assess for like how fast your code runs in the context of a machine that's basically, if you get the benchmark and you've got the actual server running on the same computer, there's contention for CPU cycles and that sort of thing. And so you get all this noise introduced into your data. And with a single sample, typically, you get into this scenario where it's like, okay, I can't even apply statistics to this to understand the distribution of those response times to figure out if we've actually got a real change or not. Okay, so since that was essentially too big of a mountain to climb, we bailed on that. Okay, and so the next thing that we tried at a high level was basically co-opting the integration test framework. And so similar to how the end-to-end test framework operates, the integration tests are a suite of tests that exercise specific components specifically at the API level, typically, although we can reach in to the server if we really want to, but we tend to avoid that. And the approach that we took here was to try to basically create another wrapper over this this base class, essentially, that would start up an in-process, in-memory web server. And we used benchmark.net to facilitate the benchmarking. And so here we ran into another set of maintenance problems, as well as this kind of limitation around the statistics, which is like, it's kind of like the tests are generally designed to be pretty minimal. We're not looking to modify the test. We'll run the test multiple times, but we don't necessarily have a lot of state in the system to kind of give us that sort of like feeling of how well the system's operating when there's actual user-like behavior, because that's more or less what we're interested in. It doesn't need to be like a full, like enormous database necessarily, but we want to have some approximation here. And so the overarching issue here, like the theme, is around the maintenance. Okay, it's like really difficult to maintain these systems. I think we introduced the benchmark.net approach back when, oh God, it would have been like a year and a half ago. I think it was when we were introducing .NET 5, and there were all these breaking changes in terms of how we were compiling Octopus Server. We were making major changes to how we even did that internally. Benchmark.net had its own issues with how it compiles and how it actually creates the jobs. And then, unfortunately, there were these limitations around user experience, like the dev experience using benchmark.net. It's a great benchmarking framework, of course. However, there's some limitations with respect to sort of this sort of application of that. In particular, it's kind of difficult to like debug tests and that sort of thing because they run out of process, which means that if you're running the test, you have to attach to like a completely separate thing. And it's not sort of in the one space you're working in inside of the IDE. If you're running sort of like a unit test, you can just debug that test. It's not quite the same with benchmark.net. So with all of these learnings and experiences, I kind of developed this vision around having a tool that was a little bit more, that was very much like benchmark.net, but a little bit more simple. It didn't have all of the hyper optimizations that library provides, but also, but did have sort of this, like a familiarity to it, I suppose. And so I came up with this idea of Sailfish, which is a benchmarking library. It allows you to write tests, so you can sort of see one of these example minimal tests over here on the right. If you're familiar with benchmark.net, this probably looks kind of familiar to you. It's modeled after that library. But it allows our developers to write tests in a way that is familiar and also like can be run directly in the IDE. So if you're interested in this, you can go to the documentation website, links over to GitHub if you're keen to have a look at the code. It's all open source, so feel free to have a look. But the main project goals here, I want to illustrate what these specific goals were. Right, the first thing was that I wanted to have a standard API for assembling performance benchmarks in the same way that like benchmark.net provides a standard API. I wanted to provide an experience similar to some of the common unit testing frameworks that are available to .NET developers, like XUnit or NUnit. And if you're familiar with unit testing in general, it's typically nice to be able to run these tests directly from your IDE. And so with Visual Studio or JetBrains Rider, you get these nice play buttons next to your test. And so that's what you get with Sailfish. And it also outputs, all the logged outputs come right into the test output window. So if there's exceptions, for example, when you're debugging or if you're running the test, or if it finishes completely, you get all the statistics printed out there and all the results. We'll have a look at what that looks like towards the end of the talk. Importantly, it also provides like a library that doesn't really require much maintenance because it's pure .NET code and it's very simple. Yeah, so it's got a low maintenance overhead. But importantly, it enables usage as both a test project, like your X unit or N unit, but also as a library. And so what you can get, like what you can do with this is you can basically have a solution where you've got a couple of projects. I'm assuming that I'm talking to people who are familiar with sort of these things. But basically, you can have two things sitting side by side. A project where you've got all of your tests. And you can develop those tests. You can run them directly in the IDE. You can configure them. You can do all the things that you need to do to get those tests running against whatever target. And then you can have a project that sits next to that serves as something like a CLI, where you can reference those tests, and then you can, say, containerize the CLI with the tests and then invoke it. So that gives us a lot of flexibility as both a good developer user experience, as well as something that can fit into a tracking system. And so that's what we get at Octopus from this library. Gives that familiar tool to our devs. So it's more or less really simple to develop one of these tests, but it also fits into a performance tracking system that we'll talk about next. Cool. Okay. Now this is like what we're actually doing right now. And so this is pretty cool. The performance tracking system. Okay, so this tracking system is basically a multi-component system. It's a few microservices that run, and this diagram kind of expresses what the system looks like. It's all code, obviously, but hopefully this picture will suffice. Okay, so the way that this works, I'm gonna walk you through this diagram here. All right, so first we've got some sort of end user or some sort of trigger. Maybe we've got a user who wants to execute some tests against a particular version of Octopus Server, and they'll trigger the test via some UI or via a request. Or maybe we have a trigger that is in our CI pipeline. So this is how the system is currently being triggered. So what will happen is we'll make a request over to this test run orchestrator component. This is an API. It's just a web server that is responsible for orchestrating the runs, basically, and also keeping track of the data and then doing any analysis on that data. And so what will happen is the trigger will come in and the orchestrator will make a request to this other web server, the infrastructure controller. And this is a multi-purpose. This wasn't built specifically for the system. We've co-opted this component. But what this does is it allows us to stand up infrastructure in a cloud provider, like Azure, for example. And so when we make the request, it'll go and create some either containerized or non-containerized services. So for example, in this case, it'll go and create a resource group, and it'll use the Azure Container Service to spin up an Octopus server with a SQL server next to it, and then kind of wire these up together. And then credentials for accessing that server will be returned back through the controller down to the orchestrator. And so now we've got some infrastructure stood up, a live Octopus server instance ready to go. Maybe there's a backup database that's been restored. Maybe it's a fresh database, And then the orchestrator will say, great, now I've got these credentials for accessing the server. I'm going to pass those off to this Sailfish test runner. And so it'll invoke another container. So this is always going to be a containerized service, which holds the tests in the CLI that I mentioned before. And then it'll execute the tests. And that will make timed requests against the Octopus server. And once it finishes, it'll take the results, post them back to the orchestrator, save them into the database. And then the run ID, so this is all sort of like fire and forget. So as soon as you make the request, it'll return a run ID, and the end user or the system that's triggering it can poll for the completion of that run. And then when it's finished, they can either retrieve the raw data, or they can take a run from a previous run and compare it to the current run. And so this is how our tracking and analysis system, this is how we monitor for regressions. We say, cool, we had the run from before. That's this ID. And now we've got this ID for the run that we just did. I'm going to send those back to the orchestrator, and I'm going to ask it to analyze the two of those. And we'll employ various statistical methodologies as well as heuristics to determine whether or not there's an actual regression. And we'll layer in controls to assess for noise in the system and that sort of thing. And we're generally trying to achieve sort of an approximation of how well we're performing, as well as whether or not we have any major regressions coming through. And that's the system. That's pretty clever. I think it's pretty cool. Cool. All right. So I mentioned that all of this is in the cloud. Okay. So I think everybody here is probably going to be thinking, boy, geez, that seems kind of risky. There's going to be challenges associated with this. And you're right. There are some pretty significant challenges associated with assessing performance, in particular when you're using cloud infrastructure. And there certainly are going to be limitations to what you can actually achieve here. Okay, so as we talk about some of these challenges, the first thing I just want to kind of illustrate using my fantastic diagrams here is that, we have to ask the question first, like, what is the context in which we're benchmarking, assessing the performance? Okay, so when I think of APIs, I always think of like a sphere, and the sphere is, it has these holes on the surface, requests come in, a bunch of stuff happens inside, and then the request exits. And that sphere exists in the context of all of this, either the infrastructure on your local host or whatever. And so this diagram here is basically illustrating this to the best of my drawing abilities. I'm not really an artist, so forgive me for this. But anyway, these arrows coming in are arrows coming into these holes at the API surface. So all of the requests will come in through the feature space, and that's all the endpoints. And then what happens is, no matter what feature you're using, that request is going to pass through some sort of cross-cutting functionality. So whether it's the middleware, or whether it's the persistence layer to access some data in the database, or whether it's passing through the caching mechanism that's applied to a lot of our endpoints, or maybe there's a message bus or something like that. Like there's this cross-cutting features that are always going to be present in your API, and so these requests will always pass through those. And then this sort of behavior of the request sits inside of this broader context, pre-existing state in the database. For example, if you're going to go and scan a table, the amount of time it takes for that request and response to complete is going to be contingent on how much data is in a particular table when you need to scan the table. If there's more data in the table, it may take longer to get through that. And then there's background activity. So I mentioned the task system that we have in Octopus Server previously. There's a lot of background tasks actually that are going on, and depending on how much activity there is, different users coming in and doing things on the server, background, like which background tasks are enabled, how much data there is to process within each of those tasks can affect the response time. This, of course, sits within this network situation. These requests have to be made across networks, which then sits inside of this broader infrastructure context, the machines themselves and the providers of those machines. And so let's talk a little bit about the biases from this infrastructure. Okay, we're not going to go through an exhaustive list. I mean, that's not the point here. The point is to just kind of share, it's like, hey, there's a lot of things, and this is just a few of them. And you'll notice that a lot of these are out of our control. So for example, resource sharing, you have to be deliberate about how you choose the machines that your software is going to run on, right? The Octopus Server instance. Can how much can you control for noise in that aspect of the system? Physical location. If I'm making a request from Melbourne, so I'm in Australia at the moment, Melbourne to Sydney, that request might return a little bit quicker than if I'm making a request from Melbourne to London, say, or New York, or what have you. So physical location comes into play. Thermal throttling can get you. When computers get hot, they slow down a little bit, right? It's not much you can do about that. Network bandwidth limits. Cloud providers enforce their own limits across a lot of their features. A lot of their features. There's network path variation, disk I/O performance, CPU and memory type, virtualization overhead, security layers, encryption, that sort of thing. List goes on and on and on. So all of these can introduce bias into your results, which you have to either mitigate or control for. So this image here, I'm going to share a couple of plots in this talk. So this image here is demonstrative of this sort of noise that you might experience. So what we did as part of this sort of proof of concept, I suppose, is we built a minimal system, and then we stressed it like crazy. And we ran, I think it was like 15 performance tests not in parallel, but like individual. We stood up, I guess, 15 resource groups, you might say, and then invoked 15 different test suites against those. And we did this, I think, around 1,800 times. Let's call it 2,000 times. And so each line here, so there's one line here you can see. Each of these little blops here are lines, vertical lines. And what you're looking at is the standard deviation, one standard deviation for the distribution that is returned for each of these tests. And so what that means is, we have a test, we execute it 15 times, we've got an array of 15 numbers, that's our distribution, and then I can look at the standard deviation of that distribution. And so typically, this is one of our control tests where we're just looking at, it's like a thread.sleep or something like that on the machine in the test. That's all we're doing. And you can see here, typically it completes pretty much instantly, which is what you'd want to see for this control. But every once in a while we get struck by a meteor, So I think this happened one time in 2,000 tests. So what's the chance of being hit by a meteor in this context, where suddenly we're waiting around 50 milliseconds for no good reason, really? It's about 1 in 2,000. Okay. Our system needs to be able to mitigate that or handle that or recognize when that happens, because this might lead to something called a false positive. And that's something we really want to avoid when we're trying to give our developers feedback on whether or not their code changes or slowing the product down. So the system is not the only thing of concern for us, of course. We also have to think about the product itself. And so what we have to do is assess application behavior biases. Unfortunately, the reality here is, I've written here, not all tests are created equal or suitable for automated tracking. And so hopefully you can see the tiny text here. It's not really too important. The idea is that we've got 6 individual tests that we've analyzed. So this is part of that experiment where we've sampled the system, thousands of times. And then for each of the 2,000 runs, we've collected all the results from that and plotted out a distribution of the entire range of response times we might get for this test, just to get a sense of, can we even use this test or this set of tests that we've already established? So I'm going to draw your attention away from this first one. We'll come back to this in a second. But the things I want to point out here are that typically we've got a single peak for most of these tests. And oftentimes the distribution, the range of minimum to max runtime value. So you see here on the x-axis, we've got the runtime for the test. This is all in milliseconds. It's a histogram, so the y-axis is just the frequency for that particular bin. But you can see, like, typically for this test, we're around maybe 200, 180 milliseconds. But every so often, we get up to about 400 milliseconds. Okay. So that's a problem that we need to deal with in the system when we're analyzing for regressions, because this is against the same version of server over and over again. This is the actual distribution of response times. And so if we've got a sample that falls within this distribution, it very well may be a real result and may not be a regression. So we need to be careful. You've also got, so we'll go back to this first test here because this is really interesting. You've also got some of these behaviors in server which are, quite frankly, somewhat surprising. We've got 2 peaks instead of 1 peak. So this is what's called a bimodal distribution. And so that means that the system generating the data, server plus all the infrastructure and everything, has 2 modes of operation for this test. Sometimes it runs kind of slow, maybe between 40 seconds and 60 seconds, and that's to create 10 machines in Octopus Server. And then sometimes it runs faster. Not as frequently, but just sometimes it just runs faster. And so if we're sampling from this distribution, sometimes we might sample from this mode around 20 seconds, 25 seconds. And then sometimes we might sample from this distribution, maybe around 60 seconds. 20 seconds to 60 seconds might seem like a regression, but in the context of the real distribution for this particular test, it's actually not. And so we can't really use tests like this that have bimodality, multimodal tests. But at the same time, the big picture here is like, we can't really, it's about sensitivity, really. Like, how sensitive can we be in detecting a regression? Cool. Okay. So ultimately, once we've curated our tests and we've got the system working and it's, firing against every commit or, every version that we try to ship, what does this give us? What are the impacts of this and benefits? So the first thing is that we get visibility and trends. This is really important. We can see kind of the performance for each individual test. And again, we're focusing on these cross-cutting, if I haven't emphasized this strongly enough, we're really focusing on the cross-cutting concerns of the product. So we're not so interested in I think it's like 400 different endpoints. We're not going to try to cover that because that's a maintenance nightmare in and of itself. We're going to really just have a few tests that focus on exercising the core functionality, the cross-cutting functionality of the server, the caching mechanisms, the persistence abstractions, these sorts of things. And we get insights on whether or not we are breaking this for regressing in these components. And then we can also create some safety nets around the core functionality as well. So we can get some notifications if and when a clear regression is introduced that slows the product down. And so on the right here, you can see some plots that we've got in one of our internal dashboards. It gives us insight into one of our deployment preview endpoints. So this is one of our hidden endpoints, but you can see that we are stable over versions. So these are the different versions. And I think this is the last 50 versions or so, give or take. So that's what it gets. And the visibility thing is really important as well, because like I mentioned earlier, we had some changes to our caching mechanisms. And it's not just that we were able to detect the regression, right? The power behind this is that we could see that we could test the change. We had a version of server where some changes to the caching mechanism were made. We exercised the test suite against that new version, and then we were able to compare before and after that change, and we could see what the actual difference was after drawing many samples. And then we could make an educated decision, a strategic decision around whether or not we were willing to accept that change. Ultimately, we were, right? And the point is we were able to see that and actually have the information we need to make the decision. And that's what's key. Cool. Okay, so that's the tracking system, right? That's around speed. Now I want to talk a little bit about scalability. Okay, so this is going to be around assessing scalability using machine learning. I think this is particularly exciting, so I hope you find this exciting as well. And what we're going to do, I'm not just in general, we're not here to give a lecture on machine learning or anything like that. I think it's a fascinating tool in our toolkit that we can leverage. But what I want to do here is give an example of how we can use machine learning to assess scalability. So we're going to walk through sort of the steps that we took to kind of produce a result. And the question that we're going to ask is, how well do tenanted deployments scale? Okay, so the technique we're going to use is first model selection. There's two techniques. One is model selection. We're going to assess the complexity of this particular behavior, I suppose. It's not a single endpoint, but it is actually. So we're going to assess whether or not its complexity is linear as it scales. Do we experience linear growth or log n growth or quadratic growth, things like that. And then once we have a model selected, we're going to perform regression to create a model that we can use to make predictions. Okay, so we'll see exactly what I mean by all this in just a second. The data that we're going to use are sailfish execution results. And there are a couple of caveats. Okay, so first is that this is a non-rigorous example. Okay, so this is a real experiment that I did. I did do it for the purpose of the talk, but we're probably going to use it as well internally. We may redo the experiment, but what I mean by non-rigorous is, I wasn't super careful around turning off all the other processes on my computer or getting a very clean machine to do this on, making sure there's like very minimal noise and that sort of thing. But we did take a lot of samples, as we'll see in a moment, and we did perform outlier detection and remove those. And so it is a pretty stable data set, and we'll see what it looks like in just a moment. The other caveat is the data from this particular experiment tends to be heteroscedastic. So that's a crazy word. What does that mean? It means basically that we can be less certain about our predictions at higher scales. In technical terms, it means as your x value on your plot, as your x value increases, the standard deviation of your data tends to increase. We'll have a visualization of what that looks like. And so the other thing is that this is based on simulations run on my local computer, so my laptop. It doesn't account for things like the auto-scaling infrastructure that our cloud platform has for Octopus Server and all that sort of, all those bells and whistles. This is just like on my machine, when I'm running a single instance, not a cluster of Octopus Server on my laptop, how well does this scale? All right, so those are the caveats. Alrighty, so the first thing was to write some tests. I'm not going to show you the code for the test because it's kind of just like code, I suppose, and we're not going to talk through that anyways. But to give you a sense of what Sailfish looks like when you're using it in the IDE, if you're familiar with JetBrains Rider when you're running unit tests, you can see it looks pretty familiar, right? We've got all the tests here, and we can see the scale that we're running at. So when there's one tenanted, one tenant for the tenanted deployment, that's a tongue twister right there, I think. I think there's 5, there's 10, 20 tenants, 50 tenants, and 100 tenants. You can see the outputs from one of these tests below. We've got some descriptive statistics, the mean, median, the standard deviation, the min and the max. We've got the outliers presented here, as well as the distribution. So these are actually the actual results from the tests. So basically we did some setup, and then we said, great, we've got one tenant, deploy to that tenant. Cool, create 4 more tenants. Now we've got 5 tenants, deploy to all 5 of those tenants, and do that 50 times, right? And keep track of how long it takes. And that's what these numbers down here represent. So we ran this over and over again. That's something you can do with Sailfish. Okay, so once we've got the data, we can then have a look at the result. So the first thing that we did is plotted what's called a kernel density estimation plot. So that's another fancy word, I suppose, in statistics land. But basically what it means is, what's the distribution look like for your data? So as I mentioned before, our data is heteroscedastic. And what that means is that when we're at small values over to the left, so you can see the blue here is 1 tenant, over on the right is 100 tenants, and it's just 1, 5, 10, 20, 50, and 100. That's what each of these peaks are. On the left side, we have really tight distributions. There's not a lot of spread. But as we get higher and higher in the scale, we tend to flatten out and be less certain about where the actual value is. We have a wider range of response values for this. And so you can imagine as you continue to move up and up and up in scale, it'll just get wider and wider. And so your confidence decreases as you increase your scale. Okay, so that's a limitation, unfortunately. But we'll see in the next plot that it's not such a bad thing. It's not so limiting. I guess the next slide, I suppose, because the next thing we're doing actually is model selection. So we run our, there's a feature in Sailfish called Scalefish. So yeah, that's a thing. Anyway, Scalefish helps you perform model selection based on results like this. Okay, so this is what one of the outputs from Scalefish looks like. We've got our tenanted deployments. And essentially what I want you to focus on here is just the best fit. It's a linear growth model. That was the best fitting model that we found. And then you can see the goodness of fit metric. And then we've got the next best goodness of fit that you can see over here. And you can see it's pretty close, but not quite as good as the linear model. And so what we'll do is we're automatically perform the regression. So this kind of happens at the same time, technically, model selection and the regression, because it's the regression that allows us to select the model to produce the goodness of fit measure. But the actual model that this produced is right here. And I think probably most of you will be familiar with the form of this model. F of x equals mx plus b, right? It's just your high school algebra, really. The machine learning component to this is that we're able to learn what this number here before the x is, and then what this negative number over here is. So that's the learning bit. And so we're able to regress and achieve a model that is f of x equals 67.16 times x minus 716.46. Cool. All right, now if I want to make a prediction, all I need to do is take my scale into account. Say I measured up to 100. Maybe I want to predict 1,000. I plug 1,000 in for x, and then that's my result. And so what does this look like? If I plot things out, this is a plot of linear growth and runtime for tenanted deployments. My duration here is on the left. So that's my y-axis, 20 seconds, 40 seconds, 60 seconds. And then on the x-axis is the number of deployments. And so each of these violin plots, that's what these are called, they show the distribution of results at that particular scale. My line was basically fit through these, and you can see it's not perfect. It's not right through the center. It's not exactly through the center, but it's pretty close. It's the best fit line that we could produce during this regression. And so once I've got this line, I can say, great, I know exactly how this is going to scale. It's linear, thank goodness. And then, yeah, we'll just plug the numbers in. And that's what this is here. Cool. All right, so what are some actual predictions that we've made? I think this is like really, really cool. So I'm geeking out a little bit talking about this. All right, so for 300 tenants, for example, we'd expect that to take about 7 minutes. So we saw on the last slide, I'm gonna actually go back really quickly. For maybe 50 tenants, it took about, I don't know, 70 seconds or so. For 100 tenants, it took on average about 150 seconds. Okay. So if I scale that up to 300 tenants, well, then it was probably going to be, plus or minus a few minutes, about 7 minutes. 500 tenants, it might take about 12 minutes. At 1,000 tenants, maybe around half an hour, plus or minus 10 minutes or so, something like that. 10,000 tenants, now we're getting into the 4+ hour range, plus or minus. Let's say we want to get up to 50,000, because that's one of our key objectives, is like we're trying to support 50,000 things. 50,000 tenants. Can we get the system in a state where we can support this? And so I think that the real, how do I want to articulate this? Like the power behind this, like what makes this so useful, is that it's not just about us knowing whether or not we can scale. It helps us understand what kind of promises we can bring, right? If we have a customer that says, "Hey, Octopus Deploy, we need to do 100,000 deployments in 24 hours, like every single day. We have to deploy our software to 100,000 tenants. Can you do this? We can look, instead of spending 24 hours to actually do that, to see if we can, or longer if we actually can't, what we can do is use machine learning to make predictions about this. And we can say, well, based on these predictions and our confidence, it looks like if we do 100,000 deployments, it's going to take us around 40 hours. So we're probably not ready to take that on quite yet. But depending on how much you pay us, we can talk priorities, right? Or something to that effect. But anyway, that's kind of that's the utility here, which I find really interesting and quite exciting. Okay, so I'll finish this up by saying, just reminding that these are predictions, so they're approximations. If we did 50,000 tenant deployments, would it actually take 20 hours? Probably not, because we're drawing from a sample. We know approximately how much time it should take. But I do think that it serves as a decent starting point, both for conversations with customers, as well as internally to understand our own product and how well we scale. Cool. All right, well, that's it from me. Thank you so much for hanging out. I hope you've been enjoying this event. I think it's pretty exciting for all of us internally. So thank you so much for spending the time to listen to what I have to say. If you have any questions, feel free to reach out. You can, find us somewhere. I'm on LinkedIn. You can contact the company and that sort of thing. But yeah, enjoy the rest of the event, and hopefully we'll see you in person at the next one.